This is part 2 of for the examples for section 5.7, 1 and 2, triangle inequalities. We just finished example 5 in the previous video. This is example 6, but we're still going to be using the triangle inequality theorem. And so that's the one that says that any two sides added together should be greater than the third side, and therefore you have a triangle. In example 6, if a triangle is proposed to have two sides that have lengths of 5 and 8, what is the range of possible lengths for the third side? Now, although the previous example we had all three sides to work with, in this one we only have two sides, and so we're trying to figure out what number can be in the range of the third side. So to get a visual of that, take a look at these several different diagrams here. If we want to create a triangle with 8 feet, an 8-foot side and a 5-foot side, like it says here and here, it could be a very small side, but at some point there's a number in which it's not going to be any smaller than. So here's another example. Notice the side that's 5 feet long is starting to, the angle here starting to get bigger and bigger. The 5 feet stays the same each time until finally we've stretched it out into a very obtuse triangle until finally at some point this third side is going to be too long to fit for the sum of 5 plus 8. So this is what we're doing here. We're comparing to see what range of these numbers could be possible. So by the triangle inequality theorem, we still do it the same way, except this time we're going to let x equal our third side. Since we only have two sides to deal with, x will be our third. So using the theorem, we'll start with 5 plus 8. It should be greater than the third side x. Also, 5 plus x should be greater than 8. And finally, the third combination, x plus 8, should be greater than 5. Solving each one of these inequalities, similar to the way we solve equations, 5 plus 8 is 13, is greater than x. And we'll get back to this in a minute. 5 plus x is greater than 8. Solve for x, we subtract 5 from both sides, we get x is greater than 3. Over here on the third one, we subtract 8 from both sides, and we get x is greater than negative 3. Now, once you get to this point, you take a look at each inequality and see if it works. This says x is less than 13. 13 is greater than x, so x is less than 13. So I could write x is less than 13 here. This says x is greater than 3. So if I come over here, I can use this x and say it has to be greater than 3. Now this last one we cannot use because x is a length. And since x is a length, it cannot be negative. So this one doesn't work. This is impossible. So these two are compile our range of numbers, and we put it in a compound sentence like this. So the range, again, of numbers that this third side could be, the lengths, is any number between 3 and 13. X is greater than 3, but less than 13. Greater than 3, but less than 13. Any number in between there could form that third side. Example 7. Use the Hinge theorem to make a conclusion about two sides in both triangles. Here we have triangle SAK and triangle OYU. Recall the Hinge theorem says that if two sides of one triangle are congruent to two sides of another triangle, so there's one of our caveats, SA is congruent to OY and AK is congruent to OU, so we have that covered there. And the included angle between those two sides are not congruent. Notice that the angle between these two sides is 90 degrees, and the angle between these two given sides is 70 degrees. And since 90 is not the same as 70, side SK, we'll get to that in a minute. Since those aren't the same, that's what's required for us to use the theorem. So if two sides of one triangle are congruent to two sides of another triangle, and the included angles are not congruent, which they're not, then the theorem says the longer third side is opposite the larger included angle. So we can now say, because of this, since angle A and angle O are included, opposite those angles are side SK, and opposite this angle is side YU. Since this is the larger of the two angles, SK must be greater than YU, since 70 is smaller than 90. So our conclusion is SK, the length of SK has to be greater than the length of YU. The Hinge theorem. Example 8. Example 8 says, what is the range of possible values for x? So here we have two triangles, and they share the same side. So we know that SU in both triangles is congruent. Notice that we have two sides and another two sides in both triangles are congruent. When that happens, that's our hint to either use Hinge theorem or the converse to the theorem. In this case, they're asking us for the possible values of x. X is part of one of the angle values. The Hinge theorem had us concluding that sides were of different length. This is going to have us conclude that angles are of a different length, so we can figure out what x is. The x is part of one of the angles. So in this one, we're going to use the Hinge converse, just the reverse. So by Hinge converse, so let me state that. The Hinge converse says if two sides of one triangle are congruent to two sides of another triangle, we just got through saying they were, and the third sides are not congruent. So the third side would be this one and this one. These are obviously not congruent, or not equal to each other in length. So ST is not congruent to RS. So when all that's true, then the larger included angle, so the larger included angle must be across from the longer side. So therefore, you know 60 has to be greater, since 15 is bigger than 10, has to be greater than 5x minus 20. Once again, since RS is longer than ST, then the angle opposite the longer one has to be bigger than the angle opposite the shorter one. So this is the shorter one, so that we can write 60 degrees is greater than the measure of this angle, 5x minus 20. Now once you set up that equation, we can now go ahead and solve for x. So we can add 20 to both sides. We get 80 is greater than 5x. Then we divide both sides by 5, and x is less than 16, or 16 is greater than x. Recall, the only time you flip the inequalities when you divide or multiply by a negative, and so this is not a negative, so we don't flip that around. Now this is what we call the upper limit of the range. So we use the Hinge converse for the upper limit. So in other words, x can go all the way up to 16, but it can't be any bigger than 16. So let's write x has to be less than 16, but greater than, and we need to find this number. To find that number, we use a little common sense here when we use our lower limit. What I meant by common sense is this: any angle measure of a triangle must be greater than 0. You're not going to have an angle any smaller than 0 degrees, so we use that fact for our lower limit. So to use that, we say the measure of angle TUS, this one right here, has to be greater than 0 degrees. The measure of angle TUS again was 5x minus 20, so we plug that in. It's greater than 0 degrees. And we saw this inequality. This will give us our lower limit for the value of x. So adding 20 to both sides, we get 5x is greater than 20. Divide both sides by 5, and x is greater than 4. So this is our lower limit. Our upper limit was anything all the way up to 16, almost to 16. So this x is greater than 4. X has to be greater than 4, but less than 16. Our range of values that will work for x here, so that this makes this true, is any number greater than 4, but at the same time less than 16. So any number 4.1, 4.5, 5, 7, 8, 10, 12, 13.7, 15, whatever. All those numbers will work. Hinge Converse. Our last example, example 9, is a proof. Complete the given proof. Given that BA, the length of BA, is equal to the length of DE, and BE, the length of BE, which is right here, is greater than the length of DA, which is right here. I'll use 4 there. Notice that AE and EA in both triangles are the same. So we have two pairs of sides in both triangles that are congruent. So at some point we can use the Hinge theorem or possibly the Hinge converse, depending on what they're asking for or where we go with it. They want us to prove that the measure of angle BAE, this one right here, is greater than the measure of angle BEA, this one right here. So we start off with our given, or part of our given. Let's do this. BA, the length of BA is equal to DE. Of course, that was given, and we've marked our diagram. AE is equal to AE. Well, segment AE is congruent to segment AE, so the length of AE is equal to the length of AE. This is still the reflexive property, but instead of talking about congruency, we're talking about length, so that's equality. So reflexive property of equality. And so we have that marked. Now that we have the two pairs of sides, we can say that BE is greater than DA. That's given to us when we've marked it. Statement 4, the measure of angle BAE is greater than the measure of angle DEA, this one on this part of the triangle. So this triangle here, this angle, and the angle between the two marked sides here and here, and the angle between the two marked sides here and here in this triangle, they're saying that this angle is larger or greater than this angle. Do you recognize where that's from? Those angles are in between the two given congruent sides. That's from the Hinge converse. So the Hinge converse allows us to make this statement. Now that we know that, we can use angle addition to say that the measure of angle DEA is equal to the measure of angle DEB, this one right here, plus the measure of angle BEA, this one right here. This simple angle addition. This angle plus this angle is this angle. Angle addition postulate. Now that we've established that, we can connect the angle we're looking for with the angle in this other triangle, now that we've split them up. So the measure of angle DEA is greater than the measure of angle BEA, and that's by the comparison property of inequality. And finally, we can make the statement that the measure of angle BAE now is greater than the measure of angle BEA. If you take a look back at statement 4 and statement 6, we have if the measure of angle BAE is greater than the measure of angle DEA, and the measure of angle DEA is greater than the measure of angle BEA, then the measure of angle BAE has to be greater than the measure of angle BEA. Do you recognize that pattern? That's the transitive property. Instead of equality or instead of congruence, it's of inequality. And we have successfully proven that these two angles compare that way.